Here we are again. Now that we've learned a little bit about types of energy and the law of conservation of energy, we're going to learn now about something we call mechanical energy. And it's very simple. Mechanical energy is equal to the total gravitational potential energy plus the total kinetic energy in a particular situation. And so we can short form that, and we can say that E mechanical energy is equal to the gravitational energy plus the kinetic energy. And so this is kind of important, and I'll show you why. Let's go back to our roller coaster. We had a roller coaster car that was going all the way down and finished it down here at the bottom along the ground. So here's the ground. And we'll put our roller coaster here. We said at the start, the roller coaster has a certain amount of height. And this height is what gives it gravitational potential energy. At the start, that's the only kind of energy it has. But what happens to that gravitational energy? Well, it turns into other kinds of energy. By the time the car gets to the bottom, it has no gravitational energy left. But because the total energy has to be the same at the bottom, the gravitational energy can't just disappear. What happens is it turns into other kinds of energy. So, most of it, I'm going to get a very thick, I'm going to try to get a thick line here. Can't get my, whoops, that's color, thicker line than that. Well, it's not working right now. Anyway, I'll make a thick line by you know what, give me 1 second here. Okay, I figured out how to get a thick line. So watch this. Most of the EG is going to turn into, nice big thick line, now I go over here and make that thing again, is going to turn into kinetic energy, EK, kinetic energy. But there are other kinds of energy that are also going to be produced. One of the things is sound. Sound is energy because it's produced by vibrations. So there will be sound energy. Actually, I'll write these in a different color so you can see what the point I'm trying to make is. So we have a little bit of this energy is going to be sound. We will hear the clickety-clack of the wheels as they go down the track. There will also be a little bit of heat. The wheels rolling on the metal tracks will warm up from friction. Not a lot, because rolling doesn't have a lot of friction, but there will be some, and heat is another kind of energy. There might also be energy because as the cart is moving through the air produces air resistance, right? Or friction with the air. And so, and there could be others as well. There could be other bits of energy that are being lost. The point we're trying to make is that under average circumstances that happen for us, these red things are pretty small. These are all very small amounts of energy. And so most of it will become EK. So what we can do to make our lives a little simpler is we can just pretend the red stuff is too small to be noticed. the amounts of sound and heat and so on are not going to take away much of the energy at all. And so then, if we do that, the only two bits of energy that matter are the Eg and the Ek. So that's where we get the idea of mechanical energy. It's the kinetic and gravitational potential energy of a system or of a scenario. And it ignores all the other tiny little things that may or may not be very big or important. Of course, what you have to realize is you can only use this concept of mechanical energy when the sound and the heat and other forms of energy are small. If they're big, you have to look at it from a whole different approach, and you have to somehow add them in. But we're going to stick to scenarios that have them very small so we can keep things simple while we're learning. And we're simply going to look at the total mechanical energy of a roller coaster, ignoring things like sound and heat and friction and air resistance. Okay? Good. So we've already seen that the Ek and the Eg have to add up to the total energy. In our last video, we said that the total mechanical energy, well, in fact, we also said it in this video, the total mechanical energy is equal to the total Ek plus the total Eg. Right? Kinetic and potential. So, the trick is, how do we figure out how much energy is kinetic? Well, Ek, kinetic energy, can be calculated based on an object's speed, because it has to do with moving, and its mass. And it turns out that the relationship is 1/2 mv squared, where m is the mass of the object, and v is the speed of the object. And if you multiply the speed squared times mass, divide by 2 for the half, that'll tell you how much kinetic energy you have. And kinetic energy, in fact all energy, I'll just put it over here on the side, is measured in a unit called the joule. So after you do this multiplying and dividing, you end up with no longer kilograms and meters per second and all that. It turns into joules, or just capital J for short. Eg is also calculated in a certain way, but it's different. Eg doesn't care about fast because it's not about speed. It's your mass, but it's multiplied by gravity. It's your height and the way gravity works. So G is the strength of gravity near Earth's surface. You'll remember G because we talked about that before when we did the force of gravity, Fg equals mg. So in a sense, these two things together give us the force of gravity, which makes things fall. And the other thing that's important is how high you are or your height. So m is still mass. G is 9.8. It's the its funny full name is the gravitational field value. And it's only that value near Earth's surface. But that's all a bunch of heavy stuff. We don't have to worry about that. We know that its value is 9.8. It's also sometimes referred to as the acceleration due to gravity, but we don't put the minus in. And there's an important reason for that. Energy is not a vector, so direction doesn't matter. Energy is like money. You know, money doesn't go in a direction. If money goes from you to your friend, from your friend to Walmart, like I said before, and from Walmart to the manager, and then the manager goes and buys gas, there's no real direction. It's just going all over the place. It's spreading around. So we don't put a minus 9.8. We just use the value of 9.8 for G when we're talking about energy in this way. And then height. And so what we'll do is a couple of examples. Here are some examples. One, a truck, a 1,500 kilogram truck is moving at 20 meters per second. What is its kinetic energy? Or maybe a better way of saying that is, how much kinetic energy does it have? How much kinetic energy does it have? And the way you would solve that is by using the formula that we have learned. Kinetic energy equals 1/2 mv squared. The m is the 1500. In the question, there it is, 1500 kilograms. And the v is the 20 meters per second squared. So if you put this in your calculator and multiply it, you'll get first v squared, which is 400. And then if you multiply 400 times 15, or 1500, you'll get 4 zeros. See, 1, 2, 3, 4. And then 4 times 15, which is 60. And you'll still have the half. We didn't do the half yet. And so that would be a half of that, or 300,000 joules of energy. It's quite a bit of energy, doesn't it seem like a lot? And that's because a truck that's very massive and moving very fast does have a lot of energy. Try to stop one and you'll find out. Right? Here's another example, example 2 for the other equation. Let's say that a 20 kilogram rock is on a ledge. Whoops. Let's do the spelling thing. A ledge that is 40 meters high. How much gravitational, I'm just going to put potential energy, you know what that means by now. How much gravitational potential energy does it have? Well, now we can use our other formula for gravitational energy, mgh. The trick is, if you're talking about height, you must be talking about gravitational energy, because it has an h in it. And if you're talking about speed, you must be talking about kinetic energy with the v in it. So you can tell which kind of energy just by looking at the question. If it's talking about height, and it's gravitational. If it's talking about speed, it must be kinetic. So, if we look at our question, we have a 20 kilogram rock, that's the mass. The value of g is always 9.8 if we stay near the surface of the Earth, and we will. Then you multiply that by 40. Right? So, if you multiply 20 times 9.8, you'll get 196, I believe. And then if you multiply that by 40, you will get 24, 36, 38, about 784, I'm thinking, is what that would work out to. And just because I've been known to make mistakes, we'll try it on the calculator just to be safe. Oops, I forgot a 0. 784 and this little 0 right there. See, it's always good to check. Joules. So that's how much kinetic, or how much potential, gravitational potential energy a rock would have sitting up on a ledge. All right. I'm going to give you a couple of questions just to practice these two formulas separately. And then, in our third little video, we will put them all together and start looking at the total mechanical energy of the roller coaster and any other system that we might come across. And so there'll be a little bit of an assignment attached to this one, and you'll be able to look at that in the assignment section and complete that as quickly as you can.